class.
Okay, so the paper I want to share today is about the possible carbon dioxide above the thick aerosols of the exoplanet GJ1214b. So we know that the sub-Neptune planet have the radius about 2 to 3.9 times of Earth radius, and this is the most common type of planet in the Milky Way. But unfortunately, there's no such object in our solar system, and the motivation of this paper is the bulk density of a sub-Neptune cannot be used to constrain the composition in detail. So that's why they need the atmospheric spectrum to analyze the composition of the atmosphere. So in this study, they focus on the exoplanet GJ1214b. This is a sub-Neptune planet with 2.7 Earth radius and a mass of 8.2 Earth mass, and it is covered by aerosol, the thick aerosol. So that's why there's no a spectroscopic feature in the previous study, and in this study they used the JWST near transmission spectrum with a coverage between 2.8 to 5.1 micron to analyze the atmosphere of this exoplanet. And they use two different data pipeline, which call T-shirt and Eureka. So in figure 1, this is the 2D light curve from two different detectors. So the top row is detector NRS2, and the low panel, the bottom row is NRS1. So the column A is the normalized flux, and column B is the differential time series. So it showed a decreased flux at 4.3 micron for the NRS2 detector, and near 2.8 micron for the detector NRS1. So for the panel D, this is the residual panel. It's obtained by subtract the light curve by the model. The model is in panel C. The panel here, they calculate by using the starry model. And next, in figure 2, they show the transmission spectrum of GJ1214b planet. And in the top panel, you can see the orange data point is from the Eureka pipeline, and the blue data point is from T-shirt pipeline. They also show the two fitting line using two different models, which are chemically consistent model and free retrieval model, and also the flat line. So here they see two features of carbon dioxide around 4.3 micron and 2.8 micron, and another peak of methane around 3.3 micron. And then next, to evaluate the model preference for carbon dioxide and methane feature, they implement the Bayesian model, and their result suggests that the the presence of carbon dioxide with 2.4 sigma, and the presence of methane is preferred at 2.0 sigma. So I forget to mention that in their observation, the sigma is, let me check. Oh, the sigma is 3.3 sigma for the T-shirt part, for the carbon dioxide, and 3.6 sigma for the methane. Yeah, and in their conclusion, they said that they already analyzed the transmission spectrum of this exoplanet and compare with the Bayesian model. But the problem is the signal from these two data pipelines too noisy, and it's not enough to constrain the composition of the atmosphere in detail. And another thing is the peak at 2.8 micron. They said that it's most likely affected by the systematic of the JWST near spec bandpass used in this study. So and another thing, another result they found is with the feature of carbon dioxide is strongly detected than methane. So it indicates that this exoplanet has very high metallicity, around 1,000 times of solar metallicity, compared to other exoplanet, for example, like K2 18b, TOI 370D. So they only have the metallicity around 100 to 200 solar metallicity. And from from two issues I mentioned before, they said that they need the follow-up study to evaluate the high metallicity feature of this exoplanet. And actually, their follow-up study already published in January, and maybe next time I will present this paper to see how they evaluate the high metallicity of this exoplanet. So I think that's all for this paper. Are there any questions?
What's the main difference between two pipelines?
Let me see.
In figure 2?
In figure 2.
It's a slight difference, systematic difference.
Yes. I'm not sure if it related to the algorithm, how they do the pipeline for these two data sets. Yeah, but actually they provide the line curve fitting and data extraction in the appendix for these two data sets, like P1 for the T-shirt line curve extraction. So I think they write in detail in this appendix. But actually, I'm not an expert, and due to the time limit, so I skip this detail. So any more questions from online people?
Thank you, Terry. I have a question.
Yes.
So, what is special about this research?
You mean the motivation of this research, right?
Yes.
Sorry, my Google Meet is stuck. Hi, Yuri, can you hear me?
Yes.
Oh, sorry. I have technical problem. So
Okay.
let me share the screen again.
Okay.
You can see my screen, right?
Yes.
So the motivation of this paper is because the bulk in that density of the sub-Neptune cannot use to constrain the composition of the sub-Neptune planet in detail. Because the exoplanet GJ1214b is covered by the very thick aerosol. It's block the light, and so that's why they cannot observe and analyze the spectrum of the atmosphere in previous studies. And this study, they use the JWST near transmission spectrum. So they is allowed to analyze the spectrum, analyze the spectrum to know the composition of the atmosphere. Yeah,
Oh,
but
that means like this is the first time sub-Neptune atmosphere was investigated thanks to the JWST's special spectrum analyzer.
sorry, can you say that again?
Oh, yeah. So the unique point of this paper is because this is the kind of first time that the atmosphere of sub-Neptune was investigated using the JWST. So that is related to the Sonjin's question. So what is the difference between the normal spectroscopy and this transmission spectrum?
Yeah, but Songjin question is he asked about two data pipeline they use in this study, which are T-shirt and Eureka.
Oh, I see. Yeah. So what is the difference between the previous one and this transmission spectrum?
I didn't check the previous study, but here they use the transmission spectrum, but they use two different data pipeline. But the detail were written in the appendix. They show data instruction and how they fit the light curve. Yeah.
Okay.
Yeah.
Thank
This
you.
is, yeah. The technical is so. But due to the time limit, I skip this detail.
Oh, okay.
Terry, can I ask a question?
Yes, please.
Okay. So can you go back to the main result, spectrum figure, spectrum?
This one, right?
Just a moment. Yeah. So I think the two pipelines return consistent result, I think, just with some systematic offset. My question is whether about the so in this work, kind of methane line and also CO2 line at the smaller wavelengths looks like questioned. So what? So I think this is one of the best effort to do this kind of atmospheric observation, right? So why? What do they discuss the potential explanation for some inconsistency with this naive model and observation? So, for example, we see some enhanced data point around 3 micron, which is not expected from the model. Some data points are much high above the theoretical model. So, what kind of expectation or explanation do they have for these unidentified data? Unidentified potential run feature.
So for the sub-Neptune, usually they find a peak of water around 2.5 to 3.5 micron. But in this work, they cannot find the peak of water. So they rule out the scenario of the pure steam atmosphere. So, but for the peak of 2.8 micron, they said that it may be affected by the systematic of the bandpass. JWST bandpass they use in this study. So they are not sure if this peak is real or not, and because and it's also because of the low signal to noise ratio.
I see. And I got it. So for this source, are there anything they can do in the future? This source is already done, or some additional future spectroscopy may help understand the atmosphere of this source.
Actually, in their follow-up observation, they talk about the metal dominate in the atmosphere of this exoplanet, and it's already published in January. So so the combination of these two studies suggests that this exoplanet could be the first member of the new planet category, which is the super Venus, because the mass of this exoplanets is higher than Venus, but the atmosphere has similar feature, like they have carbon dioxide, the thick aerosol of carbon dioxide. But I haven't read this new paper.
Okay. So maybe this has already led to a kind of discovery of a new population. Okay. Thank you. I record to the kind of another paper. Thank you so much.
So I think it's time to move on to Chungjing.
Yes. Can you hear my voice?
Yes.
Yeah. Yes.
Okay. Thank you. Let me share my screen. Sorry for I joined the press release and I didn't have much time. So I present this paper. Although I already present last 2 week, but with this some of question is from discussion part, and I didn't look the detail. So today I want to update something else for this paper. So let me just summarize what is this paper. is new. So they are search this not do the research for this active repeating FRB 190520B, and all the observation is using the public data. They use a lot of optical or radio emission, yes, or image, and they have do the star forming, they calculate the star forming rate and something metallurgy or something star forming rate, stellar mass, yes, and so they are saying that this FRB is suggesting the young stellar population. And for this FRB, what is the special things is the ionized gas. So you can see in this figure, this is the H-alpha emission, and most of the emission is come from the north part. So this is kind of very special. And in the previous, we are talking about this figure. They comparing the H-alpha and the DM host. They use the H-alpha to estimating the DM host, and what is special for this image. So in this image, they are comparing the relation between the H-alpha and the DM host. So the relation is power law. So you can see the line is power law line, and they have parameter. The A means that the scale of the gas. So when the A is small, means the gas is very small, not very average in the host galaxy, and so it's large. When A is large, means the gas is separate around all the host galaxy. And
Sorry,
for
Johnson, sorry, let me confirm. So A is, what is A? You said the
So-
size of the gas, but what does the size of the gas mean?
yes, this A is related to the equation for this L.
No, I'm not
length.
asking. Okay, I'm not asking that equation. I'm asking the meaning of A.
So it's the path length through the gas sampled by the FRB. Yeah,
so
this A is this L.
Sorry, so the A is the path length of the line of sight along the galaxy.
Yeah.
But isn't it too short? Because galaxy size is usually 100 kpc, right? But here the A value is just kpc.
So it means that all gas is all in this region. Not the other region. No, is the gas is very low.
Sorry, I
Right.
don't still get the point. So A is kind of the gas clamp size, or I don't know. So you said it's line of sight path length along this gas clamp.
Yes.
So, but isn't it too small? Because usually gas is extended and 2 kp. So can you go back to the figure?
Yeah. Because this FRB is very special.
Can you go back to the figure?
Figure?
Yeah, thank you.
So this figure?
But still 0.5 kpc. So the scale sizes. So what is the apparent size of the galaxy at this redshift? I mean, sorry, physical size of the galaxy, projected size of the galaxy. If you don't have the number, it's okay. Maybe
yes,
okay.
I don't
so
have the number.
This one, no? This is saying 12 kiloparsec in that the size.
12 kpc.
Yes.
So it's very, very compact. Very a dwarf galaxy, very small.
Mm.
Okay. Then I understand. So maybe so I was just confused by the scale difference. But
Okay,
it's okay.
okay.
Thanks.
Okay. So when they plot this FRB, the A is very small. Then they are thinking about this is consistent with this very special ionized gas. The gas is located very small scale, but they also compare the foreground galaxy. They calculate the foreground galaxy, but actually they didn't calculate. They use another paper, use this Lee. I think it's use this paper to get the foreground galaxy cluster, and the DM host will exist, reduce to this blue dash line. So they want to say why in this FRB A is very small because of this ionized gas. But when they care about the foreground galaxy,
So Jonchin, sorry. So when you say the A is small because of the ionized gas, what do you mean? So the number density of the ionized gas is so high, so the integration lengths can be very small, something like this.
because the ionized gas is almost in the north part. The north
Yeah.
part is three times of the whole galaxy.
I know. So that in this left panel with blue contour, the location of the FRB is the yellow cross.
Is indicated, yes.
Okay.
Yes.
So my question is how? So you said the path lengths can be very small because of the enhanced ionization, but how? Why? My question is why?
Why?
Yeah, why? I don't simply understand your statement. So ionized gas density from observation, we don't know the kind of number density of the ionized gas, right? DM is the number density times the length.
Yes.
So I guess, so you want to say the number density of the ionized gas at the location of FRB is very high. Therefore, for fixed dispersion measure from the host, we can expect very small path lengths. Is it something like this?
Yes.
Okay.
Yes,
now I get it.
Yeah.
Thanks.
Sorry, my bad explanation. Yes.
It's okay.
Yeah.
I confirm.
Yeah. So they want to say the path along life side is very short, but when they compare the foreground galaxy, the length will become large. So they are why this happen. They are explaining because the large uncertainty of the temperature measurement and the off-center distribution of the ionized gas. So that's why they cannot rule out the possibility that DM host is primarily contributed by the ionized gas of the host galaxy. So this
Ah.
is what they are showing this figure.
I
And
see.
another thing is the PRS. So so what is the PRS? So PRS is a persistence radio source. So of some FRB like 12, 11, or 2, for a very similar location, they are not detect the burst, phased radio burst, but also detect something radio source, but the life scale is longer than the burst. So it's not flash, it's long life. So this called the PRS. But I think I'm not very know the theoretical of the PRS, and in the lecture they are saying the PRS is the original of PRS is unknown, and there are something physical that saying PRS is because the pulsar wind nebula or the signatron nebula hit by the FRB emission, or correlating the mass black hole with the low luminosity. So these three reasons will cause the PIs happened. So this FRB have also detected the PIs, and they are discussing with the PIs. So in the previous work, uh, they are also working at PRS, but in this work, their conclusion is different. So in the previous work, they're comparing the star forming rate divided from the radio emission. So in the previous, their conclusion is the PIS is the highly obscure star forming region. But in this work, they are comparing the electron temperature, this TE, of the ionized gas in the host galaxy, and they found is higher than the typical warm plasma. And when they estimated the temperature, is the lower limit. So they are thinking about their conclusion is this temperature is imply that the radio trans highly obscured the star forming region could either be compact source embedded within the ionized region, or that the radio emission is not primarily due to the star forming. Yes. Star formation. Yes. So this is they are discussing the PRS. Yes, that's all.
Thank you, Jongjin. So are there any questions?
I have a.
It's okay.
Sorry.
You go.
Thank you, thank you. Mine is quick. So at the end, they discuss temperature, right?
Yes.
What is the value of temperature? They don't show number. They are saying they estimated the temperature, right?
Yes.
What
Let me.
is the temperature? Here.
I need to find.
Could you go back to table? This one, stop.
Yes.
3 times 10 to the 4. Okay. Maybe this is higher than standard HT region. Usually people say 10,000, right? So
Yeah.
this is 30,000. Okay. Thank you.
So can you go back to the main figure? So in this for this source, they didn't detect PRS.
PRS, yes, they detect. PRS is in.
Sorry. They detected?
No, it's not this team. Other they use the public data.
Okay, yeah,
So
sorry, I'm not talking about other source. I'm talking about this source.
yes, yellow course is the FRB location, and the circle, yellow circle is PRS location.
Which is yellow circle?
This one, this circle and the cross.
Circle and
It's
the
very
cross
nearby.
is it the location of FRB or PRS?
Cross is FRB and the circle is PRS.
Okay. Okay. So there is PRS. So can you go back to the main result, main figure,
Main
showing
figure.
that with figure showing DM versus something?
Okay. This figure, yes. Is this one?
Yeah. Okay. So can you show the entire figure? I don't see the entire figure. So can you show?
Entire figure?
I mean, I don't see the upper part of this figure in my environment.
If this is
Okay, thanks. So where is so my point is basically we never know this DM host is mostly coming from the warm ionized gas or the hot gas, maybe even hotter gas in the persistent radio source region, right? So I think this is, in general, this is just upper limit. So I think the data point is upper limit, and then, for example, in case of FRB 121102 with similarly bright PRS, in their case, we know that rotation measure is huge and coming from the PRS region. So I think that maybe the contribution to the dispersion measure from the local PRS environment, smaller scale environment, might be high. So in that case, if the same thing is happening here, then maybe this FRB 190520B, the constraint here can be even, I don't know, DM host or maybe some fraction of DM host might be from local environment. Then this estimate can be just the size of the ionized gas is just a lower limit, right?
yeah.
DM is upper limit and A is lower limit. So it can be much, I don't know. So basically, we can never solve the degeneracy between the TE measured in this work. It is just looking at the global scale of the galaxy.
Yeah.
But so I think I just want to see where FRB 121102 is located on this panel. I want to see the comparison. So this source is special. This source is very.
Hi, Sutaro.
Yeah.
Due to the time limit, so I think we should move on to Tomoki presentation.
Sure, of course.
Yeah. So you can continue the discussion after this.
Okay. Yes, they didn't put the comparison. Yeah. Okay. I think maybe change to the next person.
Thank you, Georgie.
I can see my screen. I think.
Yes.
Okay, I'd like to introduce this paper, which shows the second scale periodicity in active repeating FRB source. And here is abstract, and they observe FRB, this guy, yes, this guy, and they find that they find the 1.7 second periodicity in this FRB source, FRB source, and they use 2,800 FRB detected FRB during 49 days. And okay, here the question is that they find in the observation for 49 days, they find this periodicity in just in 2 days, and in other parts they cannot find any periodicity like this second. And this is a question, personal question for these detections. And using observed period and period time derivative, they calculate spinal luminosity and magnetic field and such kind of things. And they find that the magnetic field is 10 to 15 Gauss and age is 44 years. And so it's consistent. So this result is consistent with the Young magnet scenario for this FRB source. And let's move on figures. Okay, this one. This is the time when they observe, and they mainly they use fast, this green and blue bars. And from this for these each days they conduct periodicity search, and just in these 2 red days they find periodicity. So on the other days they cannot find such kind of periodicity, and so I think it's very how to say it is a kind of mystery of this finding. But at least they say that they find this periodicity in these 2 days about maybe 9 sigma or 10 sigma, such kind of things. Here is the result of periodicity search, and these are for oops, sorry. Okay, these are for non-detection date. Here is such sigma limit, and they conduct folding search, and not power, not search for powers. They only fold the pulse and search periodicities. And here is non-detection day, and these two are detected days. And they say that here is for these 2 days, it is above 8 sigma. Here is 8 sigma or maybe 9 sigma or such kind of values. And they report that the period is 1.77 seconds. And because they find period in these 2 days, they can evaluate the time derivative, so time change of these periods. This is used later. And also, they find some periodicity, but there is still some small sorry, there is still pulses that is out of this periodicity, and they fit this the right curve here, and they claim that almost strong FRBs are within this phase, and these outliers are relatively weak pulses. So there may be some strong emission region and weak emission region, or such kind of a bit complex configuration might be realized in this source. And here is second one. From this observation from this observation, they find period and its time change, time derivatives. And from these 2 values, they can evaluate its magnetic field and ages. And this is very shown here. And this is very near to the known galactic magnetars, is magnetars here, but a bit maybe high field. And this direction is the strong. This direction is the magnetic field, and this direction is the age, and a bit younger than other galactic magnets, but maybe consistent with other magnets. And here is the detected bursts. Okay. Maybe that's all. Sorry, wait a minute. I think I don't miss any important information. So, oh, okay.
Thompson, I have a question.
Hi.
Oh, figure 4.
Oh.
I just wonder. I want to know details of more about the observation. So So what is the integration time for each day?
Integration time.
Okay. I get too confused because in this figure 4, so this time of arrival is from 0 to say thousands, right? So this is say hours. I wonder if they have continuous observation, say hours observation per day, and they repeated this every day.
Actually, I can answer.
Thank you.
So basically, CHIME is so first has mostly continuous observation each day. However, sometimes there are occasional interruption observation due to calibration. So I'm not sure if in this selected period there is some maybe some suspension of observation in between. Usually, continuous observation is conducted every day over hours. So I think it is.
And then I also wonder, so figure 4, so the signal appears only at a certain time of arrival, right?
So could you repeat again?
So I can see strong peak in figure 4. Figure 4. Then this peak happens at a certain time of arrival.
Maybe here? Along this line?
No, I'm talking about one single peak. That one.
This one?
This one. This is significant, right?
Yes.
This happens only at a certain time of arrival. But then, are they saying this periodicity is found over the entire exposure time of this day?
Yes, this day. Because this is all of these black sculpts are detection, and it is within this phase.
Okay. I see, I understand. So basically, this black means detection periodicity.
This black means maybe something like light curve.
Oh, yeah, but then if it's stronger, that means periodicity is more significant, right? No? The brightness of FRB?
This is similar to famous Hausser diagram. So I think this doesn't show any periodicity.
This doesn't show any periodicity.
This is just showing light curve evolution along time.
Yes.
Okay. Then one peak corresponds to one FRB?
Yes.
And I have a comment
okay. I see.
on his question at the beginning. Maybe why they detected the periodicity only in two selected period. This is probably because periodicity is around 1 second, order of 1 second. This is if you put all the FRB bursts on the waiting time distribution, I think we have read some very small number statistics below second scale. And each day, I think they detect maybe tens of, maybe 100 or tens of fast Fourier bursts. But these bursts must be detected within very kind of short period of time. So the burst detected in this analysis must be clustered because we are looking at a very rare smaller waiting time first. So I can easily expect this kind of periodicity is not always detectable. So maybe they tried in each observation and they only had got kind of significance on only selected day when burst happens in a clustered manner. That's what I guess.
Yes.
I'm not sure.
Okay.
Yeah. So just having large number is not enough. The large number of bursts must happen in a clustered manner.
Okay.
Over a short period.
You mean that we should observe in like this sequence?
Yeah.
You
So
mean?
basically,
Okay.
this kind of sequence must not be sparse. This must be dense enough.
Okay. If it is sparse, we cannot.
But
It is.
But from this, it looks very, sparse.
Yes.
To me, this looks very sparse.
Also, you can see sometimes kind of some bursts are separated very kind of close. Right? So maybe these close pairs are enough. I mean, we have a lot of close pairs. So I think
the number of FRBs in this figure is very small, no?
If we have enough number of close pairs, it's okay to detect.
But in this evaluation, they just do foldings, not do conducting power spectrum calculation or such kind of things. So if this is the part is FRB is clustered, then if we calculate this kind of plot, then I think if there is periodicity, it may be clustered in this small region. I think.
But we don't know whether this is something like accurate pulsar, right? So I don't know if the beam is pretty wide, then we can expect this kind of huge distribution in phase. Pulsar radio emission is also something like this, right? So it's not always have the same phase. So maybe I'm also confused. Even if you fold pulses, not FFT, folding pulses, I think if you have enough number of cross pairs, if you have enough number of cross pairs, it should be okay.
I think it should be okay, but if there's many cross pairs, but if we hold like this, then I think if there's periodicity, we can find this kind of lines. Is it correct?
Yeah, I think so.
Oh.
It should be clustered in phase.
The Astrophysics today.
Sorry.
Thank you, speaker, Tomoki Chongjin.
Thank you.
So, we need to decide who will present the paper tomorrow. So, are there any volunteer? Yeah, thank you, Tomo-san. Anyone else? Oh, thank you, Sotaro. So, Sridhar, can you present the paper?
Sorry, maybe I can talk about the A-tail FRB situation, what's happening right now.
Yeah.
Something about Euclid? People from NTHU. Yes. I just wonder, somebody wants to present a paper on Euclid?
Maybe I can.
Because not all of us may join the dedicated Euclid meeting. So maybe I just wonder what's new and what kind of thing we can do as a non-expert.
Okay. I'll try to summarize. That's a good idea. Thank you.
Thank you so much.
Good idea.
So we still need 3 speakers tomorrow, right?
Yes.
Yeah. So Srida, can you do that, right? So tomorrow we have Tomo-san, Sotaro, and Srida. So thank you everyone for joining today, and see you next time.
Thank you.
Thank you.
Bye.
Bye bye.